Hello class, welcome to chapter 9. We're looking at 9.1, which is to simplify and use square roots. And we have three objectives: simplify expressions with square roots, approximate square roots, and simplify variable expressions with square roots. Okay, so let's focus on the very idea of square roots. This concept comes from the idea of squares. Okay, it's nothing but the reverse operation of squares. So we have the definition right here. We're saying if n squared equals m, then m is the square of n. So let's take maybe a number. Let's use 5 squared. 5 squared is 25. So they're saying if 5 squared equals 25, then this 25 is the square of 5. So I replace the n and the m with some specific numbers so you can actually see how the definition works out. Then let's look at the square root of a number definition. Well, we'll use the same thing, okay? So if 5 squared equals 25, then 5 is the square root of 25. Looks like a play of words, but you can actually see what direction we're looking at this. So if it is a square, then the large number, right, 25, is the square of 5. So when you multiply 5 2 times by itself, that gives you 25. So you squared it. Square root will actually reduce the value, so it's going to be the smaller number. So 5 is the square root of 25. So if you take the square root of 25, then you're asking yourself, what times itself will give me that 25? And you realize the number is 5. So based on that, we will now look at the notation. Square root notation, very distinct. You have this special symbol. This symbol is called the radical sign. And whatever goes under this symbol, okay, so they use the letter M. So the M could signify anything. It could mean a letter, a number, anything. And let's say, excuse me, 25. Then 25 is called the radicand. Okay, anything that goes under the radical sign is called the radicand. Okay, so if it has more than a specific expression, like if it was not just a 25, but say 25 x squared, then all of it becomes the radicand. So let me write that out here. Let's say I have 25x squared. Then this entire thing, 25x squared, becomes the radicand. Now, maybe I'll throw in a negative sign inside. 25x squared with a negative. Again, they're all under the radical sign, so you have that the whole thing as radicand. Okay. If I had a minus outside the radical sign, that doesn't matter as radicand because it's not under the symbol, it's outside the symbol. Okay. So I hope that is clear. Now let's use that symbol to understand this. Now this symbol is also found in your calculator. Well, this is called the square root symbol, right? Square root notation. The radical sign can be found in a calculator, and you could use your calculator right away to get the answer. So we'll do both ways, okay? Now for square root of 1, if you pulled out a calculator, and again, depending on the type of your calculator, you may be asked to first enter the radical sign and then the number to get your answer. That's in most recent versions. If you're using a very old calculator, then the order in which you enter would change. You'll have to enter the number first and then the square root symbol. So just understand how your calculator works. And anyway, that gives you the answer here as 1. Square root of 1 is 1. But if you're seeing this as a, not using a calculator, but as a mathematical concept, then it simply means that when you multiply 1 by itself, 1 times 1, you get back 1. That is the radicand. Okay. Now let's try for square root of 4. Square root of 4 comes out to be 2. So again, the rule is it should do the reverse, right? So if you multiply it twice by itself, you'll get back the 4, the radicand. Okay. So that is the whole idea. When you take the square root, you're trying to see what number when multiplied by itself gives you that radicand. Okay, that is right here, radicand. So you can go filling this table and reasoning it out below it as 3 squared, 9, and so on. Okay. Now, if you're thinking in your mind, what about negative 3 squared? Okay, again, you want to multiply that number by itself, right? So negative 3, if that was my number, if that was the answer I wanted to give, then you have to multiply this by the square, right? Meaning you have to multiply this twice. Negative times negative gives you a positive 9, right? Yeah. So that is the desired radicand that you see there, right? So negative 3 could also be a possible solution. Yes. Now we will come to that perhaps towards the beginning of the next chapter. But for now, if you see, come back here to the definition. We're saying, well, if you're taking the square root of m, that square root is a positive number whose square is m. So that is why we're choosing only the positive possibility. Okay, although you have the negative possibility, negative 3 when squared gives you a positive 9. We're only choosing the positive choices. So this will be 4. So that 4 squared is 16, 5. And I can go on like that. So let me fill that up. So 6 squared is 36. 7 squared will give me 49. 8 squared will give me 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. 13 squared 169. 14 squared 196. 15 is filled for us, which is 225. And you can go on. We're just doing the first 15. Okay. So this gives you an idea of having familiarity with the first few square roots helps you to resolve many problems quickly without even using a calculator, but you always have the calculator to help you out with these. Now, in all of these things, you got a perfect square root, right? These numbers were round ones. You did not have any decimals or fractions to go with it. Because these were round numbers, whole numbers, we call them perfect roots. Perfect roots. Okay. Now let's look at this problem here. We're asked to simplify 4 parts here. Let's take part A, square root of 36. We look back at the table. The table tells us for the square root of 36, the answer is 6. Let's box that. B, square root of 196. The radicand is 196. So what times itself will give me 196 is the question. I'm looking at the table. 14 times 14 will give me 196. Maybe I should write, since 6 squared is 36, since 14 squared is 196. Okay, C is negative square root of 81. Okay, what is your radicand? Remember again, the radicand is what comes under the radical symbol. So your radicand is 81 here. And that's what we're interested in finding. What times itself will give me 81? So if you come scan your table, 9 squared is 81. What about the negative? Well, the negative will tag along outside so that you have negative 9 as your answer, because we say since 9 squared is 81. Okay, this negative that's outside the radical symbol has no effect in the calculation. It just gets tagged along into the answer. So you could also see that part D requires the same kind of thinking. The negative is outside the radical, so I just keep it in the answer. And I'm asking myself 289, square root of 289. So what times itself will give me 289. Again, this is square root, so we are only multiplying it by itself. If it was, we're not looking at the other roots, but say, for example, it was cube root. The cube tells me I have to do it 3 times. I have to multiply that number 3 times over. Fourth root means I'm looking for a number which, when multiplied 4 times over, gives me that radicand, and so on. Because we're looking only at square roots here, we are totally fine in just understanding the number being multiplied by itself. Say since 17 squared is 289. Okay. Let's take a look at this problem here. Square root of negative 169. Well, use your calculator and tell me what you get. Okay. So, or you can't tell me. Meaning I can't hear you. But explore that. That gives you an idea of how it is to actually enter a negative number. In fact, you have a special button to enter a negative quantity in front of the number. Okay, like don't use the regular minus sign. Okay, because that will not. It's sometimes by fluke it may work, but that's not the way to work through that. Okay, so now, anyways, if I plug this in the calculator, it says error. It depends on your calculator. Sometimes it will say input error or domain error, and that is even more explanative. I'll just say domain error or input error. If you see this, that means what you entered in the radicand is incorrect. Okay, that's because what the calculator is saying is, well, I can find a number when multiplied by itself gives me 169, but I can't do that if your radicand has a negative in it. So this is the radicand, right? So we're asking ourselves, what times itself will give me this negative 169? Well, we know that 13 is going to work. 13 squared is 169. No problem with that. But that was not the question. The question was negative 169. So 13 squared only gives me a positive 169, right? So, oops. So, well, this does not give me negative 169. So let me try negative 13 the whole square. Well, negative 13 times negative 13 gives me a positive 169, which also does not give me the desired radicand, which is negative 169. What this tells us is there is no real number you can find that will do the trick for us. This implies there is no real number. Okay. So technically, this is kind of undefined, right? So if you want, you could use the symbol too. There is no solution to this. So it's undefined in the real number system. So there is no solution, and we use the symbol phi to indicate that there is no solution. All because you had the negative in the radicand, meaning the negative was under the radical sign. Let's look at problem B. The negative is, again, appearing, but then it's happening outside the radical. So if you were to enter this the way you see it in your calculator, you will have no problem in finding the answer to be negative 8. That's because the negative is happening outside the radical. So our problem with the radical is with the negative sign is eliminated. And so it's just the 64 that you're interested in, which is 8 squared. Okay. So anyways, let me just box these answers. And that is how we simplify square roots. These are just with numbers. We didn't see any letters coming in them, right? Okay. Now let's take a look at this problem. This is interesting because it's a play of how the symbol is understood. Square root of 25 plus square root of 144. Clearly, you see two separate terms, right? The plus in between them separates them completely. So you do them one by one. So square root of 25 is 5 plus square root of 144 is 12. So now you can add the 5 and the 12. That gives you 17. Part B has one long square root with 25 plus 144 underneath it. So your radicand is this entire thing, right? So you want to do that first. So if you were to add them, right, you get, let me put it out here, 25 plus 144 is 169. And then you take the square root of 169, which is 13. Okay. Now this illustrates that you get two separate answers. They're totally different answers because the question itself was totally different. If we are not paying attention to how the square root stretches over the number fully, or is it separated into two terms like the first problem, that really matters in how we work on the steps to the solution. So always understand that you work on the radicand first. And so in the first problem, the radicand was simply a 25 and simply a 144. So you were able to do them separately. But here the radicand was 25 plus 144, and therefore you do that first. You add them first and then take the square root. In the first problem, we took the square roots first and then added them. Next, we look at approximating square roots. This is a very cool way of doing it because you just simply use the calculator. Because to approximate, we have that problem coming in only when we don't have perfect roots, right? So if we come across numbers that do not have a perfect root, like in this case, round square root of 17 to 2 decimal places. Now, square root of 17 is not a perfect root. Okay, let me write that there. Square root of 17 is not a perfect root. That means you will not get a whole number as the answer. And if it's not a whole number, it's going to be a fractional answer. With a calculator, we get decimal answers, right? Most calculators do not give the fractional answers. They give it instead as decimals. And so that's why they say round it to 2 decimal places. So let's remember this. When they say approximate, in this case, you are using a calculator. Let's say use calculator. And so I'm using the calculator to find the square root of 17. And I get 4.123. Let me just write that out here. Square root of 17 is 4.1231056 and so on. But remember, the question says to round to 2 decimal places. So I stop at the second decimal place and look at the number to the right. That number is below 5. So square root of 17 is approximately, look at that symbol there, right? It's not exactly equal, it's approximately because we rounded it to, it's approximately equal to 4.12. And so the answer is 4.12. So again, if you want to kind of support that, 4.12 when squared gives you 16.97. Okay, let me just write that. 4.12 squared is 16.9744. Well, we rounded it to 12, so you're getting 4 decimal places. And you can see that it's not exactly equal to 17. It's close to 17. And because we rounded to 2 decimal places, you know, it doesn't give you a closer approximation. If you were rounding it to 7 or 8 decimal places, perhaps it will bring it a little closer to 17. But again, we're trying to follow the instruction in the question, which says what to do, how to round it. Let's also try this for square root of 11. Again, use your calculator. That's the only way to respond to this question. This also is not a perfect root. So square root of 11 comes to be 3.3166247 and so on. And we will round it to the second decimal place. So the number to the right is a 6. So square root of 11 approximately equals 3.32. Okay. Next, let's look at simplifying variable expressions with square roots. All right. Now we have letters coming in the picture, right? We didn't. If they were plain numbers, then that's kind of manageable, it seems. All right. Now here is the biggest understanding of the concept of square root and squares. Let's remember this. Squares and square roots undo each other. Okay. This is the whole concept. This is where the two come together, the squares and the square roots. Okay. So what do I mean by that? So if I had square root, right? It's like the root is a 2. We don't write the 2. Okay. Square root, we instead call it square root, but you know the 2 is there. We don't write it explicitly. If it is cube root, fourth root, then we put the number there. Okay. Let's say m squared. Okay. What we're saying is this square root and this square will undo each other, resulting in just an m, right? The square root symbol is the whole radical sign, right? So that radical sign and the power will undo each other because they match. Square root and square matches, right? The 2 and the 2. I put the 2 explicitly so you can see it. So let's say I had square root of 7 squared, okay? Then if you can see that what was invisible was the 2 there, right? Because it's square root. So you know that this and this will undo each other completely because they are matching, and that will give you a 7. Let's say you had square root of 2 and m cubed. Will they undo each other? No, they cannot undo each other because the powers don't match. The 2 and the 3 here don't match, right? So they cannot undo each other. So we have a different way of handling this, okay? What we would do is we would then rewrite the m cubed. I'm just putting the 2 again for explicit purposes. Then I split up the power 3 as 2 and 1, right? Remember? When you multiply two same base with different powers, then you add the powers. That was a rule we learned under exponents, chapter 5, exponents. And so we're using that concept, and so you can see that the square root will undo only this 2, but it doesn't help undo the 1, right? So this would come out as m for these two, but this m will still remain trapped under the radical. Okay, what we're trying to say here is that if they have exactly matching powers, yes, it'll work. But if they don't have exactly matching powers, then we have to do some work around it. Let's say we had m power 4 and the root is 2. How do you handle this? Well, we cannot handle this directly, because they don't match. But we do have an easier solution because the power is even, right? So you can think of this as m squared times m squared, right? So that the root cancels that, the root also cancels that. So you have two m's there, so the answer comes out as m squared, m times m. But the easier way to kind of understand this is like the m, the fourth root of m, it's like the powers got divided. The 4 got divided by the 2. So you're getting back m squared. So there are many ways to handle this if you had even powers, because that will, it can be split perfectly as powers of 2. And so you'll be able to cancel that or undo it with the square root. When you don't have even powers, then we have extra work to do. When you have matching powers, then they eliminate right away. So let's come back here, and we are looking at this problem. So square root of y squared, and let me write that 2 for the square root explicitly, so that symbol and the power will undo each other, giving us y. Okay, it doesn't matter what the letter is because it's the power that has to be worked against the root. Again, it's a b squared. Let me put that 2 there explicitly so you can see that. Again, we don't show the cancellation in actual math because it's understood. It's actually ridiculous for me to even show that cancellation. But again, remember, this is for illustration purposes, just to explain it to you much better. But when we do it in a problem, we won't show the 2 in the root like this. We won't even show the cancellation, right? Because we understand that the root and the power will undo each other. So that is a b. What about a power 14? Okay. So then again, this is a 2 here, and a power 14, 14 could be written a power 2 times a power 2 times a power 2. How many times? 7 times, right? Why am I doing the 2? Because I want the 2 to match with the root. Okay, 1, 2, 3, 4, 5, 6, 7. Well, quite obviously, you see that it's cumbersome. But then if you were seeing it in terms of the 2 canceling each term there, each factor, I would say, not term. How many a's are we left after they've cancelled off? 1, 2, 3, 4, 5, 6, 7. We're left with 7 a's. So the answer is simply a power 7. A times a times a, right? The power is 7. But this looks cumbersome. Say for the next problem, it's 24. Are you going to write it that many times, like 12 times with the power 2? Here we employ the root the power property. So we're just going to say, well, a power 7, the whole squared is the same as 14 because 7 times 2 is 14, right? The powers. We multiply the powers in the power rule of exponents. So we're calling upon the power rule so that we could actually see that this root and this power will undo each other, leaving us with simply a power 7. Right? And we want to keep it that way so that we can keep our calculations simpler. Okay. So let's attempt the next one. Okay. So I could write this as w power 12 the whole squared, because I'm trying to see 2 times what will give me 24. Well, it should be 12, right? So that this 2, the root and the power 2 will undo each other, leaving us with simply w power 12. I'm sorry, I'm kind of squeezing it there. So they both give us the same answer, but in a power 14. But I was just trying to show you that it was easier to do it as power rule. Let's focus on the other ones now. Okay, so this is 49 and x squared. Okay, remember you want the whole power here to match with the power for the radicand, right? So you're trying to do something power 2, oops, so that they will cancel each other. The root and the power will cancel. That's the whole point. So what should go inside so that that squared is 49x squared? Well, to begin with, we know that 49 is 7 squared, right? So we write that. And x squared is also x squared itself. But remember, the square is already outside. So you don't put the 7 squared and the x squared, you simply put the 7 and the x. Because 7 squared is 49 and x squared is x squared, right? They undo each other, just giving us 7x. Let's try this for the next one. So you want something the whole squared so that the root and the power will undo each other. What should go inside? Well, 100 squared is 10. So, I'm sorry. 10 squared is 100. Square root of 100 is a 10, I meant. And y squared. So just put the y because the square is already collected outside. And the answer simply is 10y. Okay, let's try it for this one. Same stuff. You want the power and the root to undo each other. What goes inside? Well, I look at 121. I know that from the table, right? We looked at the table too before. All right, so 11 squared is 121. So I got the 11. What squared will give me m power 20? So then m should take the power 10 so that the power rule applies. 10 times 2 is 20. So m power 10, the whole squared will give you m power 20. This results in simply having the other two cancel each other off. They undo each other, leaving us with 11 m power 10. I hope you're beginning to get the idea. You can pause the video right here and you could do the next 2 problems and then check with me. So what goes inside would be 25. For the 25, it's supposed to be 5 squared, so that's 5. H power 44. So 44, again, ask the question 2 times, because the 2 is already fixed, right? The 2 is fixed on the power. 2 times what will give me 44? Or you could also use the calculator and do 44 divided by 2 to get that number. Okay, that'll be 22. So H power 22. So that 22 times 2 will give you 44. And you get 5h power 22 as the answer. And lastly, '81 is 9 squared, so I put the 9. X power 36, again, figure out 36, what times 2 will give you 36, right? Or you could use a calculator and figure out 36 over 2. So that is going to come out as 18, because 18 times 2 is 36. And your answer is 9x power 18. Okay. So this just is simple, but it takes a little bit of work for you to understand that the root and the entire radicand with a single power 2 will undo each other. Okay? As we saw in this a power 14 example, if you have 2's all over the place, that's a little confusing to even capture. But if you had 1, 2 to match with the 1, 2 on the root, the power 2 and the root, then it's a lot easier both for calculation and for understanding. So that is the whole idea I'm emphasizing here. The root and the power in the radicand must undo each other. Okay, let me write it out here one more time. root, or we could say square root in this case. Oh no, let me write it generally, okay? Root and power in the radicand will undo each other. I said root and power because this could be generalized, right? If I had fourth root, then the power must be 4 so that they will match. If I had third root, then the power must be 3 in the radicand so that they will undo each other. Okay. So we will now make it specific, and we'll say square root. Okay. And power 2, right? What is a power 2? Power 2 is the same as saying square. Will undo each other. Okay. So we also have, say, if you're looking at cube root, cube indicates 3, and power 3. The root and the power, matching power. The power here is cube. Right? That's why it gets the name cube root, square root. But when you go to the fourth root, we don't have any special name. So I'll just say, if you are looking at the fourth root and power 4 will undo each other. There's no special name for this. Although we're not going to look at cube root or fourth root really, we are asking you to help ingrain this concept using other roots too. Okay, so it's mainly for square roots in this section, but remember that this will extend for any root and matching power. I hope that was helpful. See you in the next video.